Hi, class, and welcome back. So we've been talking about weathering, mass wasting, and erosion, and we're now going to focus on glacial erosion, but more broadly, glacial processes and glacial landforms that involve erosion. They also involve deposition. So we will also be talking about aeolian or wind features, coastal features, and also running water or fluvial features. But right now the focus on glacial processes and glacial landforms. So to start, what is a glacier? Well, basically it's a long, large river of ice moving downhill under the influence of its own weight. Now, these represent an enormous amount of the world's freshwater environment because they form by falling snow accumulating over time. And that snow is captured for a while until that river of ice moves downhill enough to make its way back to the oceans. So, again, glaciers take hundreds, thousands, tens of thousands, hundreds of thousands of years to accumulate that type of um, snow in the form initially of snow, compacted into a form called firn, and finally into glacial ice. So over time, that overlying weight of the fresh snow compacts the layers below it. When that is allowed to persist over time, the accumulated snow and ice gets so big that it starts to move under its own weight. And when we start to see that movement, we're now talking about a glacier. There are two major types of glaciers, those that we find in these massive continental accumulations. We call those continental ice sheets. And the other ones form in the valleys, especially in mountain environments. We call those alpine glaciers because they were first named in the Alps in Europe. So our two main types again would be like continental glaciers, and we have over here the on the right side over here a alpine glacier. Make sure my cursor show. There we go. So alpine glacier and continental glacier. Let's move on. So for a glacier to form, we have to have a zone where where snow accumulates, compacts into firn, and then compacts further into ice, and accumulates enough of a depth to start moving, to start that motion downhill. So we call this zone where we get more snow formed or falling, accumulated. We call this a zone of accumulation. And at some point downhill, there's going to be an equilibrium zone where below that, we lose more snow than what we gain every year. And this downhill portion is referred to as the zone of ablation. So the glaciers will form by snow accumulating in that accumulation zone, forcing a downhill movement because of the weight. And as the glacier moves further and further downhill, remember it's getting warmer and warmer, we start to lose more of that ice here. We will slowly lose this ice. Now, not to worry, more ice is coming from uphill because of the accumulation. So we have a constant conveyor belt of new ice moving downhill on the order typically of meters per year. Now, if we get a lot of accumulation, that's going to have more of a down slope push, and the front end of the glacier will move forward. That would be called an advancing glacier. On the other hand, if we start to lose more ice from the ablation zone than we're gaining from the zone of accumulation, then we'll have less of a push downhill, and the zone of ice will actually retreat. So we'll have a retreating glacier. So depending on the ebbs and flows of climate over hundreds or thousands, tens of thousands, hundreds of thousands of years, we'll see that glaciers tend to advance, retreat, advance, retreat, advance, retreat. Unfortunately, with climate change, we're finding that most glaciers on the planet are right now in a state of retreat, and in some cases, a serious state of retreat. So as glaciers move, we have to keep in mind that, like most fluids, because of friction along the bottom, we get the slowest movement of the glacier along the bottom where it interfaces, where the ice interfaces with rock. And as we move above that layer, we get faster and faster and faster movement. We also have friction along the sides, especially in valley glaciers or alpine glaciers. So we get slower movement along the sides and faster movement towards the middle of the channel. So basically, we'll get the fastest movements in the middle of the glacier, high above the surface and far away from the sides. We also see that because of the pressure, when ice is under pressure, it is going to act in more of a fluid motion. And when it's got less pressure or overburden, it acts in a more brittle sense. So we will see plastic flow of the glacier towards its lower reaches, or sorry, towards its deepest portions, and we'll see more rigid or brittle type of movement as we get towards the top. And that brittle movement, also moving fast, is going to create these little cracks in the upper portions of the glacier. And those cracks can open up and get covered over by loose snow. And if you're not careful, you can fall into those. Those are called crevasses. So the valley glaciers in particular, they're going to move downhill by gravity, sliding along the bottom and more of a brittle movement towards the top. Now we have to keep in mind here, we'll address this in a second, but along the bottom, you see these little boulders? Those are also going to get dragged along by the glacier as it moves downhill. That's an important concept that we have to address here in just one second. So now we see movement in the opposite direction. The glacier, in this case, will be moving from the right to the left. And as it's doing so, it's going to have two particular types of erosion that we need to focus on. Remember those boulders caught in the bottom of the glacier? Those are going to grind away at the rocks that they encounter along the way. So boulders caught in the bottom, grinding away at the irregular surface at the base of the glacier. And that's going to pulverize that rock into a very fine powder. By the way, that process is referred to as abrasion. And the product of abrasion is very, very fine, ground up silt and clay. Now, the other process that's important here is a process of plucking. Now, those large fragments of rock at the base of the glacier that have been subjected to freeze-thaw action at the base here, or broken up in many different ways, those are going to get plucked away and carried down glacier or down slope in this case. So glaciers will basically produce two very different types of rock from the erosion. Large boulders, the result of plucking, and very, very fine powdery silt and clay, a result of glacial abrasion. So again, we see here these rock fragments being torn away. I mean, think of like a very, very cold metal pole on a early morning. If you were to wet your finger and touch your finger to that metal pole, it will kind of have a sticky feeling to it. You pull away, you can feel that maybe that ice is attached to your finger and it's not easy to let go. Well, the rocks will feel the same way. These are basically being plucked away in somewhat the same manner. And as they do, they move downhill and they're scratching the base of those rocks now, the base of the bedrock. The result of that, once the ice has gone away, after, let's say after 20,000 years or so, we could have rocks exposed with these long, long, long scratches in them that we refer to as striations or glacial striations. So this is a result of rocks that were plucked and then scratched or striated the surface of the rocks below. Now that very fine powder that's a result of the abrasion, when that is in water, it gives that water a very, very powdery blue appearance many times, like a cloudy, milky blue appearance. So that glacial flour, that very fine silt and clay, will give glacial rivers and lakes that are in a glacial environment that powdery blue appearance. If you've ever been up to some of those lakes in northern Rocky Mountains into Canada, or maybe New Zealand, very, very famous for the blue appearance of lakes like Lake Tekapo near the central portion of the South Island in New Zealand. Beautiful, beautiful blue colors there. So some of the erosional landforms we'll see created by glaciers include, or some of the, I mean, there are many, many, but we're going to focus on just a few here. U-shaped valleys, that's a very typical giveaway that there were glaciers in the area, either now, and you can still see them, or maybe thousands of years later, after a glacier has receded, we can still see the evidence of that glacier there. So U-shaped valley. So imagine a valley instead of a typical V shape. Now we're going to see a valley with a U shape. So U-shaped valleys, hanging valleys, that's used to be a U-shaped valley connecting to a larger U-shaped valley, but now it's just hanging up there in a valley. I'll show you a photo of that in just a second. Cirques are like the names, that sounds almost like circle, right? So it's like a bowl of rock that had been created at the very top of glaciers that had moved away from that rock environment. And arêtes, these are sharp ridges separating glacial valleys, and horns, like the Matterhorn, is like a sharp peak created by cirques backing up into a rock face, creating this very, very steep face. I can show you that here coming up. So what do we have? U-shaped valley, very, very typical of a glacial environment. My cursor stuck for a second there, my apology. So U-shaped valley. This is the glacier, the ice carving out that U-shaped valley. But once that ice is retreated, we're left with no ice, but certainly a U-shaped valley. Now it's hard to see in this photo, but can you see a U-shaped valley up in the mountains? So that was a small U-shaped valley, and there would have been a river of ice probably at about a level here, moving off either from left to right or right to left. But this would have been a U-shaped valley feeding into a larger U-shaped valley. Well, both have now retreated, and so we have that tributary U-shaped valley up here that is just hanging up in the air. That's why we call them a U-shaped valley that is hanging, so hence a hanging valley. We see a lot of these in alpine environments that used to have much larger glaciers in there in the period of 10,000 to 20,000 or more years ago, but has since retreated as the Earth has warmed. Now, sometimes those U-shaped valleys made their way all the way down towards the ocean or the sea. And with moving out of our ice ages into glacials that we're experiencing today, what we see here is that the rising sea level has now flooded that U-shaped valley. So in places like Norway or Alaska, we will find these U-shaped valleys carved by glaciers that have since flooded with seawater. So we refer to these as a fjord. So if you ever want to do a cruise to the Norwegian coast, you'll be going up some beautiful fjords like the Sonja Fjord, or if you're looking at a cruise to Alaska, College Fjord. These are fjords, U-shaped valleys that have subsequently been flooded by ocean water as the ocean levels have risen over the last 12,000 years. So more erosional landforms. Remember I was talking about a cirque. So there would have been a glacier forming, and the top of it would have been in the area highlighted here and here. And basically as the glacier moved down slope, pulling some of those or plucking some of the rock away, it created a circular bowl-shaped feature which we refer to as a cirque. So all glaciers, all alpine glaciers, at the very, very top would have a cirque. They'd also have a little bit of a crevasse forming between that face and the glacier proper, referred to as a bergschrund. But basically, this glacial movement downslope would have formed a circular pattern called a cirque. Now, it might have a cirque here. There might be a cirque on the other side, one on the other side over here. And each of those cirque faces would get smaller and smaller and smaller over time as rocks were pulled away. But anyway, a cirque, steep-sided, bowl-shaped feature carved by a glacier moving downhill. Now, remember I said sometimes you get a cirque on one side and on the other side, sometimes three sides. Well, in that case, we would have a cirque that would create this face on one side and on the other side, and ultimately you get these steep ridge lines that are formed between those cirques, and those ridge lines are referred to as arêtes. Now, the reason we had a lot of French names here is because some of the early glaciologists were French and the name stuck. And if we get very steep peaks along these arêtes, those high peaks would be referred to as horns, and the most famous one in the world would be the Matterhorn. So basically, we have in this one a cirque, an arête, and a horn, all formed by glacial erosion of the rock that would have been there before the glacier. So this ridge line right here, we know now, we can call that an arête, leading towards a horn in the far distance. Now, whatever is taken away, whatever is eroded away, must be deposited somewhere downhill. So that fine, powdery glacial flour mixes with those big bouldery materials, and in essence, these materials are referred to collectively as till. So this is glacial till, the deposited material resulting from glacial erosion and ultimately glacial deposition. Now, we can get this in multiple forms. So till could just be amorphous, a big blanket of this material in what we call an outwash plain. Or we could have some more defined features called moraines. So a moraine is like a hilly mound made up of glacial till. Over here we've got a glacial mound, so this is referred to as a moraine, and this one would have been on the side of a glacier. So it pushes the rock material to the side, and as it pushes that rock material to the side, these big mounds develop, mounds of silt and clay and boulders all mixed together. This one would be referred to as a lateral moraine because it builds up on the side of that glacier. Then when the glacier retreats, the moraines are still there. So that's sometimes the evidence we have to show that a glacier was there in the recent past. So lateral moraines are the ones that build up on the sides of glaciers. So we have a lateral moraine here, lateral moraine, lateral moraine. And sometimes we get moraines in the middle of a glacier. Those are referred to as medial moraines. So medial kind of means the middle. Well, if we think about that, sometimes a lateral moraine can become a medial moraine. In the example in the top right, we have a lateral moraine on the side of a glacier, but when two glaciers converge, some of that lateral moraine material now becomes medial moraine material of a larger glacier. So that's how that medial moraine material, the rock fragments, actually get to the middle of a glacier. They started off on the sides, they just end up in the middle when glaciers join together, when they converge. Now remember I said that glaciers can retreat, advance, retreat, advance. Each advance will push rock material in front of it too. So we get what's referred to as these end moraines. So we have lateral moraines, medial moraines, and end moraines. Well, as the glacier retreats and advances, it doesn't always get to the same place. Sometimes it gets a little bit further downhill. Sometimes it doesn't get that far. Whichever the furthest advance took place, that will be the furthest debris moved downhill. So the furthest moraine, the furthest end moraine, is actually referred to as the terminal moraine. Think about it, that's the one that got the furthest. So we have terminal moraines as one form of end moraine. The ones that are not terminal are just referred to as end moraines. And sometimes you can get multiple moraines towards the terminus of the glacier, representing different periods of advancement. So a lot to go in there. Now we see the photographs of lateral moraines, medial moraines, etc. And if it wasn't for me, you'd see outwash plain here as at the bottom of the glacier, when the meltwater is gushing out, it's moving that silt and clay and bouldery material onto a level plane and basically just depositing a tremendous amount of till into the outwash plain. I think you've seen enough terms there. We've only got one slide left to go here, and that is that sometimes the big bouldery material being carried along the bottom of a glacier can be carried miles and miles and miles away and deposited onto what could otherwise be a rocky or even a flat material or a flat surface. So in the middle of nowhere, we might get these massive boulders that had been deposited somehow. And initially people were confused by this. How could a massive boulder this size be deposited in an environment where there's no mechanism in modern times to explain how that could move? It couldn't be done by wind, it couldn't be done by water. Well, in these environments, we have to look back into the past and say, well, look, based on, we see some striations, we see U-shaped valleys here. There must have been glaciers here in the past, and those glaciers carried these massive boulders downhill, but as the glacier retreated and ultimately melted away, it left these massive boulders. They're out of the way. They're kind of wacky. Their presence is wacky. We call these glacial erratics. So the term erratic refers to these large boulders that seem out of place in the landscape. They've been deposited there, obviously, by glaciers at some point in the far distant past. Okay, I know that's a lot to cover in just a few minutes, but that's a little bit of an introduction to what are glaciers, how do they move, what are the processes, what are their erosional features, what are the depositional features. And now if you go up to, let's say, Mammoth Lakes in that area, McGee Creek, just on the LA side of Mammoth Lakes, or if you go up into the Sierra proper, you're going to see some of these features. You'll be able to identify a little bit more about the landscape there. So good luck with that. Go travel, go see the world, and go try to make sense of why things are the way they are. Take care.